another episode of CS101. Um, I hope everybody had a great weekend. The weather here in Crawfordsville is looks like it's pretty sunny now. It was a little cloudy earlier. Um, Warming up uh, to I think it's 17 Celsius out there now. Um, so uh, getting better, not like the snow of last week. In other news, I just saw the headline that the price of a barrel of oil is gone negative because people are running out of places to store the output, which is kind of crazy. So, welcome to this crazy coronavirus world. All right, so let's get back to things. Just by way of reminder, what we were working on last time was our sort of a couple of things out of our cookbook. Um, and in particular, looks like we had done the if then else thing, and then the if then we had done here, and we had some explanation around it. Um, and then let's see. So we've got the two types of conditional expressions mostly figured out, if then and if then else. And so next what we want to do is start talking about the looping conditions. And for simplicity, I thought I would start with the do while conditional. Um, oh, there she goes. Sorry, my puppy is being silly. Um, Start with the do while looping structure. So by way of reminder, right, there are three different kinds of iterative structures, although they're all obviously going to be intimately related. For loops, while loops, and do while loops. And not every language necessarily has a construct for a do while loop. Some do, some don't. But I want to contrast sort of how do while loops and while loops, what the difference is. So let me write this in sort of Python-like syntax. So it would look something sort of like that. Now, Python doesn't actually have a do-while loop, so this isn't technically valid. But the idea, right, is that you're going to do the stuff and then check whether or not to continue doing the stuff. So um, yeah. So the difference between a do while loop and a while loop is with a do while loop, the body of the loop, the in this case stuff, gets executed at least once. It's only after it's executed that you then check the condition for whether or not to continue looping. With a straight up while loop, you evaluate whether or not to enter the loop body before you do anything in the loop body, and so it's possible for a while loop to never actually execute at all. Okay. Um, all right. So as before, condition needs to be something that can evaluate to two values, and those two values are going to be binary bit patterns of some sort, and we'll think of one of them as being false and the other one as being true. Um, and what exactly those two values look like, well, that kind of depends on how you compute the condition. So, for example, with the sample program that we wrote before, over here on the left on detecting negatives, we used um, a logical test, and um, the bit patterns that we were sort of looking at to be representing true and false were 0, 0, and 8, 0, because we were trying to extract out the far left bit of those. But it may not be 0, 0, and 8, 0 in every circumstance. It just was here. Okay, so one of those things we sort of thought of as being that representing the condition being false, and the other one representing the condition being true. Okay, so um, then what we're going to have in terms of the assembly is we're going to have the assembly for stuff, whatever it is, and this is going to start whatever the assembly for the stuff command is. That procedure has to start someplace in memory. So let's say that it starts in memory cell MN. Okay. Um, and then after we do the stuff, we need to compute the value of the condition, and then we need to have a jump statement. Okay, so this would be jump, um, and uh, the value of the condition uh, needs to be stored in some sort of register when you compute it. So let's say that that's register R, whichever one it is. Then we need to compare register R to register 0. Okay, so compute the value of the condition, load the bit pattern for, let's see, which way do I want to do this? Load the bit pattern that represents true to register 0, and then we'll do this. We'll have jump register R MN. Okay, so compute the value of the register, or sorry, the condition, and we're going to put that in register something. Okay, the jump command here is going to compare whatever's sitting in register R to whatever to the bit pattern that's representing true that's sitting in register 0. Okay, so this, if the thing in register R is the bit pattern that represents true, the jump will take place, and we'll go back up and start the whole thing over again. Okay, so in this case, there's only one jump command, and that's the one here down at the bottom, which is asking, should we jump back up and restart the loop? Yes or no? Yes would occur when register R is equal to register 0, and we want to do that in the true case of our condition, whatever true means. If the jump does not take place, then the program would go on to the next set of instructions that was after this jump, which would correspond to there being something after the do while loop. Um, okay, so save that real quick. Any questions on um, the idea here with the do while loop? And we'll do the while loop next, so for sake of contrast. See how we're doing on. Okay, Teague's typing. All right, so we'll get a question from Teague. Oh, not the greatest attendance today, gentlemen. I mean, shouldn't be yelling at you guys considering you're here, but um, yeah, kind of pathetic looking. It looks like to me. Um, got 7 people watching, and 1, 2, 3, 4, 5. 8 or 9 in the chat. Not entirely sure how that works, but whatever. Um, all right, so Teague, let's see what your question is. And take your time, no worries. I know this kind of will take a little bit to sink in. This assembly stuff is kind of complicated, but don't stop, prof. All right, so in theory, Teague asks, in theory, if you wanted to have a set of instructions happen at the same time as another set of the instructions, could you set it up so that one set of instructions loads the result in register 0, be used in a separate set of instructions? Okay, so first off, let's talk about what do you mean by the same time. Um, there is no concept of same time on a processor like the one we're working with. So um, the processor that we're working with, along with lots of processors from, oh goodness, honestly, before that were in common use before, say, 2003, 4, roughly, could literally only do one thing at a time. Okay, so our processor can only execute one instruction at a time. So having a set of instructions that runs at the same time as another one is not really possible. Now, maybe what you mean here is what happens if you have, for example, um, well, let's imagine that you have a do while loop that has a conditional inside of it. Okay, so that the checking the condition for the do while loop requires the use of register 0, but also checking the conditional requires the use of register 0. That totally can happen, okay, where you sort of inside a nested structure are having to use a register, say register 0, in multiple ways. And this is why this line right here, line 10, was so important, is that right before you do the jump, you need to load to register 0 what true means, or false, depending on which way you're doing it, um, what that means for that particular jump. Okay, so if we had, let me go over here to the if then else, right? So if we had a condition for an if then else, and let's say that this was all inside of a do while loop, then um, we might have to store, we're going to have to change what goes into register 0, okay, on the fly. And so right before you do a jump command, you need to change what's in register 0 to be the appropriate pattern, okay, for true or false, whatever that makes sense in that context. This is another reason why I said never use register 0 for anything other than this jumping stuff. Um, so that's one of the limitations of this particular processor, is that the jump commands always have to take place. Let's see, where's our list here? Always have to take place by comparing something against register 0. Okay. Um, Now, Teague, does that kind of answer your question, or at least what I thought you meant by your question? Hopefully. Yeah. Okay. Um, Now, that does bring up a good point, which kind of goes a little bit beyond this, but the reason I said like 2004, 2005, kind of in there in terms of timeline, is that um, that was about the point when computer processors that Intel and AMD were shipping started to have multiple cores, at least for the processes that they were starting to ship for consumer use. And this is the case. I mean, I guarantee basically no matter what computer you're using right now, even if it's a tablet or a phone, The processor that's in that is really multiple processors all kind of bundled into one unit. And there, the question gets stickier, okay? Because it could be the case that one core of a processor is doing one thing and another core is doing another. Now, each core gets its own set of registers, but they may have to be using the same stuff from memory. And as you can imagine, you could run into trouble if they were both reading and writing from the same sections of memory, and there wasn't something kind of keeping the orchestra in a conductor type thing, if you will. Um, so that issue of multi-threaded or where you have multiple processes doing something is a big pickle. Um, and one of the reasons that parallel programming can be so difficult is because you have to kind of keep the there needs to be some conductor to keep one part of the program or one thread, one processor from screwing up everything for the other one. Um, yeah, so parallel programming is exceedingly valuable because you can super speed things up if you've got multiple processors to throw at it. That's especially true with using graphics cards because graphics cards, modern ones anyway, are hundreds of very small, sort of purpose-built processing units. And so, certain tasks can be highly accelerated that way. Um, but taking a given procedure and parallelizing it sometimes just doesn't make sense. So I'll give you a good example. If I wanted to rake the leaves in my lawn this autumn, then I could rake all of the leaves myself, right? It would take basically all day with the size of my yard and me being fat and out of shape. Um, but eventually I would get it done. Or I could hire and get like 7 other people to come over, and the 8 of us rake the leaves. And we could do it in a couple ways. We could sort of help each other, or we could sort of divide my lawn into 8 pieces, and each person independently rake their eighth of the yard, and eventually it would be done, and it would be done, well, roughly 8 times faster than it would be otherwise. That's an example of a very parallelizable procedure. Um, and I'm sure you can think of others. But there are lots of other procedures that are most certainly not parallelizable. So a good example is, and this is kind of cheesy, um, but let's take gestation in pregnancy. So one woman who's pregnant can have one baby in approximately 9 months of time. Okay, great. You cannot take the embryo and split it into 9 pieces, implant 1/9 of the embryo into 9 different women, wait a month, and then assemble the results into a complete baby. It doesn't work that way. So that's very much a non-parallelizable process. But if you do have a parallelizable process, then on modern computing hardware, you do really have to worry about each uh, processor fighting with the other ones, so to speak. And if you're interested more in that, then we'll touch on this some in CS241. For those of you who are interested in keeping going with CS, and then especially in a parallel computing course, which at some point will run a 300 level parallel computing uh, uh, topics course. So for those of you who are considering the major, keep that in mind for future. Okay, so that hopefully clears up that. And sorry for the digression on parallel programming, but it is a fair point. we are luxurious, we have the luxury in this particular case of dealing with a processor that can literally only do one thing at a time. Uh, and processors of the 70s, 80s, 90s, kind of that era would be sort of in this category that they could really only do one thing at a time. They would just be doing it extremely fast. And so it maybe seems like they were doing more than one thing at a time, but in fact, that's not the case. Okay, so there's our do while loop. So save that, and let's make a new one, and let me save the file real quick. All right, so this is cookbook um, for a while loop. Okay, so um, our while loop would look something along those lines. So while a condition is true, do some stuff. Uh, and then when that's all finished, then maybe move on and do more stuff. Okay, so again, and I'm going to stop typing this, the condition um, needs to be something where there are two bit patterns, one of which you're thinking of representing true, the other one false, and that is stored in register R, whatever register R you choose it to be stored in. So okay, so that part of it's going to be this. Excuse me, goodness, the same as before. What's different here is that we need to compute the condition before we do anything. Okay, and we need to load register 0. Um, well, let me just say it this way. We need to load register 0 with the bit pattern that represents false, not the bit pattern that represents true. And I'll talk about why in just a second. Then we're going to jump. Uh, let's say we'll compute the condition. Um, the result for the condition being computed is in register R. Then we're going to jump MN, and this, well, actually, let me call this one XY, and then I'll say here, um, this is this instruction, if I could type today, or let me say starts in XY. Okay, so the condition, computing the condition, it may be several lines of assembly. Okay, might not just be more than one, and uh, but whatever that chunk of code it's going to start someplace in memory. Let's call that cell XY. We need to load R0 with the bit pattern that represents false, and then immediately we're going to do a jump. Now, what this jump is going to do is ask, should I enter the loop body or not? Okay, and if the bit pattern that's in register R is the let's see, I think I may have this backwards. Nope. I've got this right. Um, if the bit pattern that's in register R represents false, okay, and we loaded register 0 with what represents false, then this jump would execute. And what this jump is going to do is jump us past the loop, not into it. Okay, so here would be, we would have the stuff, well, the assembly for it. Okay, and then after that, Um, I'm sorry, this should be mn up here, and then we'd have more stuff here, which starts in cell XY. And then we're going to have another jump right here that goes back up and starts the whole thing over. Okay, so now that I've got all that typed out, let's go through. So we're going to load here register 0 with whatever we're calling the false version of the condition. Okay, and the result of the condition being evaluated is sitting in register R. If that is false, then this line would say, okay, register 0 has the false pattern, and register R has the false pattern, and that means that we should not enter the loop body. So what we're going to do is we're going to jump past it down to what's immediately after the loop body. Okay. Uh, if, however, the condition is true, this jump will not have, it will not actually jump, and then we will move on to doing the assembly for the stuff, and then we'll come down to this line right there, line 9, which is an unconditional jump that takes us back up to the start of the whole thing and checks the condition again. Okay, so um, so that's two major differences here, I think, between the do while and the while construct. In the do while, we put true in register 0. Here we put false in register 0. In the do while, we only had one jump, and in the while loop, we actually have two. Okay, so does that make sense? Any questions on that? And sorry about the barking in the background. This is what happens when you have a Cairn Terrier. But she has saved me from countless mailmen and UPS trucks and school buses and yeah. Is the main difference between the two loops where they are located in the body of the program? Um, uh, I wouldn't. I'm not sure I would say it that way. Um, the main difference between a do while loop and a while loop is whether or not the body of the loop automatically gets executed or not. So in a do while loop, the body of the loop gets executed at least once, no matter what. With a straight up while loop, the body may or may not get executed at all. Okay, so the stuff here, right? So like let's say for example that the condition that you compute here is false, then this jump would take place and you would jump right past the stuff instruction or instructions, never having done them. Whereas in the do while, you don't have a jump until right here, and so there's no way to skip past the condition or doing the stuff until after you've already done something. So the jump here is asking, should you continue, not should you do anything at all. Um, yeah. So, so slight, well, not so slight difference there. Um, okay. So, yeah. Any other questions on that one? Um, and then the last one is actually not too hard because we don't even have to write in the assembly to do it. Um, um, okay, so let me make a new file and let's say cookbook. Um, this would be a for loop. Okay, so our primitive structure for a for loop was like this. So for I in range from something to something, uh, this, by the way, just to make sure we're clear, oh, and I forgot to save this with an extension, so um, let me save this as .py. Um, just to make sure we're clear, um, that the syntax here for the Python for loop is range A to B. And what that means is that the first value of I is equal to A, and the last value of I that you evaluate is actually B minus 1. Okay, so it's inclusive on one end and exclusive on the other. Um, and I know that's mildly annoying, but, sorry, that's the way they wrote the language. Okay, so this is equivalent to writing the following. Oops, that is not what I wanted. Uh, is equivalent to writing this, assigning the initial value I to A, and then saying while I is less than B, stuff, and then doing I equals I plus plus to add 1. Well, let me just say it this way. Um, oops, and this would be more stuff. Okay, so these two structures are equivalent. Writing this in for loop kind of language is equivalent to writing this as a while loop. Okay, and so if the question is how do we cookbook a for loop, well, one way to think about it is just rewrite the for loop as a while loop, and then we've already got the cookbook recipe for how to deal with a while loop. Essentially, the only thing that has to get added is, or changed, is that the condition is some sort of inequality, okay? Namely that we want to be less than I to be less than B. It starts at the value A. And that we have a counting variable which would have to get stored in a register somewhere, uh, I, that has its initial value of A. And each time we repeat the loop, we need to add 1 to our value of I, just sort of our counter. Okay, and so, but the rest of it, this looks exactly like this, right? It's just that the condition was an inequality, and that part of the loop body was just adding 1 to a particular value. Okay, so in that sense, the for loop is nothing special because you can always just sort of think about it as a variant of a while loop, um, like so. Okay, so that actually gets that pretty tidy, and for the most part, actually, that not 100%, but that basically completes the cookbook. Um, okay, so any questions on how I took the for loop syntax and translated it into the while loop syntax? So is a for loop just a combination of an if then and a while loop? Um, well, it I wouldn't think of it as an if then and a while loop. I would say it's just a while loop where the condition is an inequality and you have a counting variable. Because notice that I never wrote the word if inside here. Um, I mean, maybe I'm being a little pedantic, but yeah. Um, okay, so now let's talk about where we're going with all of this. Okay, so I'm going to come back over to here, And let me take this file and open it. All right, so we finally get to our fun and exciting project. Um, and let me blow this up so that it's nice and big and legible. And let me um, get rid of the code there. We don't need that. Okay, so nice and gigantic. So what we're going to do is we're going to talk about an algorithm um, which you guys may have learned in, say, maybe middle school or so, which is to compute the greatest common divisor of two numbers. Okay, so this would be the largest number that divides evenly uh, the both of the two given numbers. Now, at minimum, the smallest number that this could work for is the number 1, right? Because 1 divides any integer. Uh, the question is whether or not there's a bigger number that does the job. So if I take two numbers like, let's say, 8 and 12, then their GCD would be 4. And if I took something like 8 and 13, their GCD is in fact only 1. I know that instantly because I know 13 is a prime number. Um, okay, now this concept of a greatest common divisor is super important in number theory and math of varying sorts, but it's also important in cryptography. Okay, so part of algorithms that you use to do, for example, um, encryption of credit card numbers over the internet and things of that sort rely on this algorithm. Okay, and so what the project is basically going to do is what you guys are going to do is, in a series of steps, program this thing in um, our Brookshire processor. Um, and what I have done here, and I'll post this file to Canvas here later today. What I've done is written the algorithms in Python, and what you guys are going to do is basically translate this into assembly, and then from the assembly to the machine code. Now, I should say that there are actually multiple versions of the algorithm. Okay, so probably an algorithm that you guys learned in grade school or middle school is the following. So let me take 58 and 87, which I've just chosen here as complete random examples. Um, and let me go to, say, Wolfram Alpha. All right, and if I go to, let's say, this is a method I remember learning in school, was to figure out the prime factorization of each number. So the factorization of 58 happens to be 2 times 29, and the factorization of 87 happens to be 3 times 29. So then I would say, oh, 29 is common to both of those things, and so that must be the GCD. Um, now, how many of you guys learned that particular method in school to just find the prime factorization of each of the two numbers and then take whatever's in common, multiply all those factors back together, and that gives you the GCD? Did anybody learn that method in school? Okay, Teague did. Anybody else? I know it's probably been a while. Um, I learned that method in, I think it was seventh grade math. Um, with Mr. Gibson, um, fourth period math. Uh, anyway, um, Well, okay, yeah, that's equivalent Teague basically. And yeah. Okay, so that method certainly works. Um, but it is an incredibly inefficient method. And the reason is that it depends on finding the prime factors to begin with. And this may be sort of surprising, but it's a good thing that it's true. Finding the prime factors of a number is really, really hard the bigger the number gets. Okay, so maybe a better way to say that is for taking numbers that are 2 digits large, it's pretty easy to determine the their prime factorization. Not that hard. But as the numbers get really, really gigantic, it becomes exceedingly difficult to do that. Okay, and the fact that it's difficult to do that is why it's safe for you to use your credit card on the internet. Okay, one common encryption method is called RSA encryption, named after three mathematicians that came up with it. And in the RSA method, it is commonly used in communications encryption. So take, for example, the problem of you want to buy something on Amazon, you you need to give them your credit card number. You want it to be encrypted when it travels over the internet so that somebody snooping on, the Russians snooping on your traffic don't see your credit card number and decide to buy a bunch of vodka instead of whatever it is you're ordering from Amazon. So what Amazon or what you do is Amazon chooses two really, really, really big prime numbers. And then it multiplies them together. And taking two known numbers and multiplying them doesn't take hardly any work. That's pretty quick. And then they tell you in a message, here's the product of my two secret prime numbers. You use that product in an algorithm to take your credit card number and encrypt it, and then you transmit it over the internet, and Amazon gets the message, and because it knew what prime numbers went into the sauce to begin with, it's able to very quickly decrypt it. But somebody who's snooping would have to know what the two prime numbers that they started with were, and finding those is ridiculous. Um, so, to factor, like, say, 1,000-digit prime numbers or something would take, a billion years using um, computational, uh, current computational techniques. Okay, so there's a report of the stream being frozen. Um, no, looks good to me. Um, um, yeah, so little off though. Okay, well, not sure if that's me or Twitch. Um, okay, so all right. Anyway, um, it would take basically so long for them to break the encryption that by the time that they would do it, your credit card would have expired, or everybody on the planet would be dead anyway. So who cares? Um, and so this particular method of figuring out the prime factors is a really crappy way to solve this problem. But the answer for how to solve it more quickly is actually ancient. Okay, so this algorithm, believe it or not, um, appears in basically the 3rd century BCE. So this is the algorithm that's given in Book 7, Proposition 1 and 2 of Euclid's Elements. Okay, so this is called the Euclidean algorithm for that reason. And essentially, what the algorithm does is it does a repeated subtraction. So if I take 58 and 87 and I subtract the smaller from the greater, I get 29. Okay, and then I replace the greater with that difference. So 58 and 87 becomes 58 and 29. And then I subtract 29 from 58, and I also get 29. And whenever I get to the point where the two numbers are equal, then I know I'm finished. And the prime factor, or sorry, the GCD is 29, and it's that easy. Okay, so so what I'm going to do is actually run this. Or actually, you know what? Let me um, do I have? Let me make sure I actually have Python installed on this thing. On the desktop, I should. Yep, Python 3.8. Um, okay, so I don't want to type all that stuff in, so let me actually, um, I'm used to doing this on my Mac, not my PC, so let's see what this does. Oh, same thing, it just does it in a terminal. Okay, well let me open up a PowerShell and oops, okay. Where the heck did I put my Dropbox? Oh, there it is. Okay. Teaching, or no, it's Wabash. Then teaching, then CSC101 Spring 20. Oh no, wait, this is in last semester's. So this would be under Brookshire, and I think this is binary GCD. Okay, so then I'm going to do Python 3 binary GCD GCD2.py. Oh, blast. Okay. Crap. Okay. So, um, um, yeah. So it's being ornery because of pathing. I'll have to fix that. So yes, Teague, that's exactly the how the algorithm works. You subtract the bigger from the smaller repeatedly. Uh, until the two numbers match, and when they do, the GCD is that common value. Um, okay, so I know that is kind of crazy, right? But all right, let me do this. Let me run. This is going to be a little ghetto, but it'll work. Um, work for now, and I'll fix the pathing issue in a minute. Okay, so what I'm going to do is actually, let's see if I can open. Oh yeah, here we go. Dropbox, Wabash, teaching, CS101, Brookshire, binary GCD2. Okay, so yeah, this will work. All right, so I've got this program loaded, and then I'm going to run it. Okay, and so I changed in this particular example. So let me actually blow this up so that it's a little bit more readable. Um, okay, so I don't know how visible the the size of the text here is, and I could probably sit here and uh, let's see, options, window, help. There's probably a way I could blow up the font. I'm not going to mess with that right now, but basically, I've got the algorithm, okay, and for sake of demonstration, I changed the numbers to um, 58 and 92. Okay, and then what I have over here on the right is the sequence of numbers that you get as you go through this. So if I start with 58 and 92, then 58 is smaller, so I'll subtract it from the bigger, and now my two numbers are 58 and 34. Okay, but now 58 is the bigger number, so I'll subtract 34 from it, and now I have 24 and 34. 34 is bigger, so I subtract and I get 24 and 10. 10 from 24 makes 14, so now I have 14 and 10. Subtract, I have 4 and 10. Subtract, I get 4 and 6. Subtract, I get 4 and 2. And then the next step would be 2 and 2, and that is in fact the GCD of 58 and 92 is 2. And I can change the numbers, so give me two numbers, whatever you want. So give me a couple of numbers that you want to pick. Well, let's do something fun. Let's do 1832 and, oh, 54 and 65. All right, we'll do that first. 54 and 65. Neither of which is prime, of course, so run. And here's the sequence we get there. Okay, so what I've done here is I've had it print to the console the successive differences as we go, and in this particular case, we get a GCD of 1, which is the smallest thing that we could possibly get. Um, and what this means in terms of number theory is that the two numbers that we started with are relatively prime, is we call it. Okay, and then I can make the numbers bigger, and of course this will um, still work. Okay, and there we go. Now this is not a particularly efficient version of the algorithm. But it is the simplest version of the algorithm. So let me go back to the Chrome window that has, and I'll put that there um, so that it's a little bit more readable. And then we've got our console dump here. Okay, so right. So this is the simplest version of the algorithm, okay, is just the repeated subtraction version. And you'll notice, look what kind of structure it is. It's an if-else, and within the if-else, we have a while loop, and within the while loop, we have another if-else. Okay, so this means that in terms of writing this in assembly, we can kind of think about the cookbook in the process. Um, and to sort of unwrap things. Now, the other sort of puzzle that you'll have to deal with in terms of programming this is how to tell, for example, if one number is smaller than another, or if two numbers are not equal. And by the way, um, exclamation mark equals is how you type not equals in most languages. Um, I could have also used the word not, but that's nice to Python. Okay, so this is the simplest version of the algorithm, but there are two actually slightly more sophisticated ones. And so I've put one slightly more sophisticated one here, and then at the very end, this is the most clever version of it. These for two versions essentially, and it looks like I forgot to put my citation in here. Um, these two versions, actually, you can find sort of very well, they're not written exactly like this, but as far as I know, that the uh, this special version that is slightly more sophisticated appears in the 9 chapters of the mathematical art, which is an ancient Chinese mathematical text, roughly contemporary to Euclid. I thought I had put a link to the reference in here. Um, that's my bad. I may have to just edit this. Okay. Anyway, so what that exploits is the fact that if it's the case that both numbers are even, then you automatically know that 2 is a factor of them, and you can pull that out and reduce what's left. And you might think that it's a little unfair to be using division in a algorithm that's essentially defining division. But here's where we get to be clever. So let's go back to, I know it's been a while, but the when we were together and I talked about working at Kohl's, and the fact that dividing or multiplying by 10 is really easy. You just basically shift all the bits or digits. And similarly, in binary, dividing or multiplying by 2 is super easy. You just shift the bits. So this binary version of it uses bit shifting, and that is sort of an improvement, if you will, that we can make to the algorithm that makes the algorithm slightly more complicated, right? Because we've got more stuff here, but it means that the execution of the algorithm, even for really large numbers, is much faster than it would be. And yes, that's exactly right, Teague. The bit shifting is where the rotate command would come in, asterisk, okay, because there is a difference between shifting and rotating, and I talk about that here in the rest of both in the notes and then also in this document. The final version of it uses a really clever idea, which is if you have two odd numbers, you know automatically that their difference is going to be even. And if you've got an even, you can pop a factor of 2 out of it, and bam, you can make this thing be super fly. Okay, so this is basically where the project's going to go, and what you guys are going to do is basically write 4 programs in assembly, and then also the machine code. The first 2 programs are relatively simple. It's the third and fourth programs where they start to get a little bit more complicated. So the first 2 programs are kind of steps along the way, things that you are ideas that you would need in the full program. Task 3 is to basically write the subtraction only version, and task 4 is to write the version that also uses the odd even tricks, which uses bit shifting. Um, so what you guys are going to do is basically we're going to do this project. We're not going to have a final exam. I thought we were, but it's getting too close to the end of the semester. Um, so no final. Um, if anybody's really upset about that, you can send me a stiff note via email. And so what we'll do instead basically is we'll just finish with this project and that will be that. So the whole thing is due Tuesday, May 5th, which is when our final would have been. Um, and you're going to write 4.asm files. So if you have not already downloaded Atom, the program, the text editor that I've been using, um, please do so. It's free. Um, and so you're going to submit 4.asm files, one for each task, and then zip it all up. And next time I'll show you guys how to zip files. Um, yeah. Okay, so that I think that's probably, well, we're a little over time today, so sorry about that. Um, we'll go ahead and quit for now, and I will see you guys Wednesday, if not sooner. I'll go ahead and end the stream here. Have a good rest of your day.